Hey, what's up, guys? So this is my second video about straightness and complex and constructible number. Yeah. So previously, I already discussed some previous idea that what is called a constructible number, and I proved that constructible number forms a field. And if you haven't seen the previous one, I will post a video link. Yeah, but basically the only theorem that you need to know is that if alpha belongs to constructible number, basically you can build on finite movement of the compass and the straight and the ruler, means that the f and f, if you adjoin with the f alpha, let's say you're working in some field, then this guy, the field extension is a 2 to the power, basically the degree of the irreducible polynomial over f of rho alpha. So if the degree of the irreducible polynomial of alpha is not 2 to the power, then it's not constructible. Okay, so I proved that pi is not constructible because we know that pi is transcendental, and you cannot double the cube because 2 to the 1/3 fraction is not constructible. And we proved that you cannot trisect the angle with the 60 degree because this equation ax cubed minus 6x plus 1 is not constructible. Okay, and I want to so in this video I want to explain that I previously explained that if theta is constructible, I mean if only if cosine theta is constructible. So I want to prove that I want to explain in what case that cosine 2 pi divided by n is constructible for which n. So basically this is why 17 regular Gauss is constructible, which is introduced by Gauss. Okay, hope you guys subscribe to my channel. Yeah, so this video we will prove the famous, let me just write down the theorem that I managed to prove after this video. Okay, so we are gonna try to prove this Gauss Wentzel theorem. This is E. So N, so regular N polygon is constructible. Basically, you can use the ruler in the compass to prove it. If only if n is 2 to the k, p1 up to pt, so k is greater or equal to 1 integer, so greater or equal to 0, and p1 up to pt are distinct Fermat primes or Fermat primes. Should be pronounced as Fermat. Okay, Fermat primes. Okay, and I will explain what this means. Okay, so before we start, let's do a very simple example that some particular case is not constructible. Okay, so we know that the triangle is constructible, right? Equilateral triangle, because cosine 60 is a 1/2, and then we know that the square is constructible, right? Because and this is 90 degrees, and we know that the pentagon is constructible because sine 15 is basically the square root of 5 divided by 4. So you can easily use this to construct a cosine of 100, 0, and 8. And you can do the hexagon, right? So the regular hexagon is basically formed by 6 equilateral triangles. Okay, so the first non-trivial example should be the septagon, right? So septagon. Hopefully I didn't misspelling. So basically it's that we need to investigate how cosine 2 pi divided by 7 is constructible or not. Okay, so let's prove theorem. So prove cosine 2 pi divided by 7 is inconstructible. Okay, so this is a very standard proof. Let me just write down. So you can let alpha to be 2 times cosine 2 pi divided by 7. And you can write it as z plus 1 over z, where z is exponential I 2 pi divided by 7. So we know that alpha to the square will be z squared plus 1 over z squared plus 2. And alpha to a cube will equals to z cubed 1 over z cubed plus 3 alpha. Okay, so which tell you that z squared plus 1 over z squared is alpha squared minus 2, and the z cubed was plus 1 over z cubed is alpha to the cube minus 3 alpha. Okay, we know that alpha to the 7 is 1, right? And I know that which is the same as z to the 6 plus z to the 5, 4, 3, 2, 1 plus 1 is 0. Okay, so I can write this as a z to the cube 1 over z to the cube, z squared plus 1 over z plus z squared plus 1 over z squared, and this. Okay, I know that this here guys alpha, this guy's alpha squared divided by 2, alpha cube minus 3 alpha. Okay, so you can easily prove the following. So this also minus 1. So this is the polynomial that alpha satisfied, where alpha is 2 cosine 2 pi divided by 7. And then you see that the alpha equals to plus or minus 1 is not a solution, right? So which proves that if you add joint q with this alpha with the q, this dimension is 3, is not 2 to the power. So by the previous theorem that the septagon is not constructible. Okay. Okay, so yeah, this is why septagon is not inconstructible. Okay, so now let's try to prove the original theorem. And yeah, so idea is that we defined alpha to be 2 to the cosine 2 pi divided by n. Okay, and the not trivial, but the simple group theory. So you can use a simple group theory to prove that the q of alpha at joint with q, this is equal to phi n divided by 2. Okay, so this phi n is basically the Euler number, Euler phi function. Okay, so let me just explain how to compute this phi n, and I think everyone knows it. If you don't know, I will I will give you, I will post the my group theory lecture that you can go to. So phi of n is z of n cross the number of this. So basically, it's everything. Basically, the number of the element which co-prime respect to n, which that's equal to n. So basically, I should say number of k, where k satisfy 1 to n, and k and n are co-prime, or GCD of k n is 1. Okay. So obviously that for any prime number, phi of p is p minus 1. And you can easily prove that phi of AB equals to phi of A, phi of B if AB are co-prime. Okay, and you can also basically use this. You only need to compute phi to a p to a k, and you can prove that this is pk minus 1. Okay, so this is a simple group theory, and yeah, this is called chitotomy. Hopefully I didn't spell it wrong, right? So by a cyclotomic field. Okay, so related to phi to n. So basically this is the nth roots. N roots of unity will give you some particular dimension called phi of n. So this is some number theory issue. Okay. So we need phi of n divided by 2 to be the 2 to the power. Basically, we need phi of n to be 2 to the power, right? So for example, if you compute phi of 7, which is 6, right? So 6 is not 2 to the power, so no way. Okay. So this forms a sufficient and necessary condition to be a number to be constructible. Okay, so let's try to solve this, right? So I can assume that n equals to P1A1, P2A2, up to PTAT. Okay. And so I can compute this phi of n. So these are distinct primes and with each power. So I get the P1A1 minus P1A1 minus 1, P2A2 minus P2A2 minus 1, with PTAT minus PTAT minus 1, minus 1. So I hope this guy is 2 to the power, right? So 2 to the power. Okay, but this is a distinct prime, right? So there's no way. Okay, so you get the P1 to the, you get P1A1 minus 1, right? P1 minus 1, and the P2A2 minus 1, P2 minus 1, PTAT minus 1, PT minus 1 is 2 to the power, right? But this guy are all primes. So the only possibility is that if what? If A1, if AI is greater or equal to, right? If AI is greater or equal to 2, then this guy will be P1, this guy will be P2, right? So this is impossible. The only way is that when AI greater or equal to 2, that P of I must be 2, right? Because by 2 to the power, okay? Otherwise that, otherwise, if Pi is not 2, right? The only way is that AI must be 1, okay? So from here that I can assume that our n looks like 2 to the k, and the P1, P2, PT, these are R primes. Right, but we haven't investigated what is the property of such R primes. Okay. So we now still compute this phi of n, right? It now become 2 to the k, P1 up to PT. So this guy is a 2 to the k minus 2 to the k minus 1. This guy is a 2 to the power, so I don't worry about it because this is just 2 to the k minus 1. But this guy become phi of P1, phi of PT minus 1. Phi t, so this is P1 minus 1 up to PT minus 1. And this guy is a 2 to the, must be 2 to the power. Okay. This guy is already 2 to the power. So this Pi minus this P, so this guy is even, right? Because now P is odd. Now P is odd. So this guy must be even, right? So which tell you that the P1, let's say P1, Pi minus 1 must be 2 to the power, right? Otherwise that the product will not be 2 to the power. Okay. So Pi must be 1 plus 2 to the power. So I need to find the price. I need to find, so the only the sufficient condition is that find the price looks like 1 plus 2 to the something. Okay, right? This is our goal. Okay, but so what is the form, or what is the prime number? What is the prime looks like 1 plus 2 to the something? Let's say 2 to the k. Okay, so you can easily say that if k is 3, suppose k is 3, right? Then 1, 2 to the 3 will not be prime because this guy can be factored as 1 plus 2, and 1 minus 2 plus 2 square minus 2 cube. Sorry, minus 2, right? Okay. The reason is that we have this, right? We have this xk plus 1. We'll have x plus 1 and 1 minus x plus x squared up to xk minus 1. So this guy, this always exists if k is odd. Okay, so which tell you that this 1, 2 to the k, this k cannot have any odd factor, right? So k cannot have any odd factors. The reason is that if 2 to the k has some odd factors, let's say m, then I can write it as a 2 to the something. Let's say k equals to mn. Let's say I write k in looks as a 2 to the n times m plus 1. Then if m is odd, then I will have this kind of decomposition. Then this guy is not prime, right? Because I have one non-trivial factor. Okay, so which k cannot have any odd factors, which tell you what? K must be 2 to the power. Okay, so k must be 2 to the power. Let's say 2 to n. So we need p equals to 2 to n, 2 to n plus 1, this guy. We need the prime which is constructible if and only if p can be written as 2 to the 2n plus 1. Okay, and this kind of a prime is called the Fermat primes. Fermat primes. Fermat prime number. Okay, how to pronounce Fermat? Or Fermat prime numbers. Okay, let me just call it Fermat. Okay. Okay, so basically we proved what? We proved that n is constructible. So we proved the first theorem that I mentioned in this video. Basically, any regular Gauss is constructible if n can be equals to 2 to the k, p1 up to pt, k greater or equal to 0, and p1 up to pt are distinct Fermat primes. Okay, so this is, we proved this famous theorem. Okay, so let me just give you a quick introduction of Fermat primes. Then I will use a Galois theory to explain what the hell is how to construct a 17. Okay, so let me just quickly introduce these Fermat primes. So this Fermat primes looks 2 to the 2n plus 1, right? If let's define f of n to be this. Okay. So Fermat price definition is that this f of n looks like this one. So f of 0 will give you 3. F of 1 is 5. F of 2 is 2 to the what? 2 to the 2. 17, and f of 3 is 257, and f of 4 is 65537. Okay, so all these 5 are primes, prime number. Okay, and the f of 5, which is a famous detected by Euler, basically is sorry, f of 5 is 2 to the 2 to the 5 plus 1, which is 2 to the 3 2 plus 1. This guy is a 641 times 6700417. Okay, so this guy is not prime. Okay, so up to now, this is the only 5 prime numbers. So this looks stupid that I define Fermat define something which is hopefully prime, but can only be prime with the first 5. Okay, but this is still open question. So there are many open questions. The first one is that f of n is a composite number when n greater or equal to 4. This is still unknown. Okay, and also is there finite fn is prime? Unknown. Okay, is it infinite composite Fermat? Unknown. Okay, is there exist Fermat and f of n is not square free? Oh, this is also very weird. Okay, so this is a weird also unknown. Okay, so many unknown things about this Fermat prime. Okay, so yeah, so let me so now finally let me explain how to. But so we prove what? We prove that basically we prove that 7 gun, right? 7 regular polygon is constructible, right? But how? Okay, so originally, so I need to cosine 2 pi divided by 17, right? Satisfy some a-dimensional, let's say this is alpha, right? So your Q of alpha at the joint with Q, this is 8, right? So I need to find some quadratic extension, right? By the previous, I want to find some quadratic extension Q such that the Q and the Q alpha, which is 8. So I need to find a field extension, right? So what is the technique to find a field extension or finite extension? Basically using our lovely Galois theory. Okay, so Galois theory, I cannot tell you here that what is the precise definition, but basically the idea is basically the subgroup of Galois group will want to run corresponding to the immediate field extension. So field extension. Okay, so idea, so in this case, that's this, you can imagine that your Galois field, your Galois group start from Z17, and which is so basically you just view from 1 to 60. Okay, and your intermediate subgroup will corresponding to a field extension. Okay, so idea, I want to find an intermediate field extension such that which is dimension 8. Okay, so this is very weird, right? So I start from a 1, which is a trivial group, which is a subgroup of 1 and 16. Okay, so this is -1, because remember we are in the mass 17. Okay, and so this guy will corresponding to let me just wait. So this guy, so when group enlarge, you are in, so this guy will be some Q alpha. Okay, will corresponding to Q alpha. Okay, and the least guy will become some subfield, which I don't know what hell is going on, right? But basically some subfield, let's say something. Okay, and this guy can still keep extending, right? So notice that dimension is 2, right? Because this is the Z2. Okay, so you can, so what is the next step, right? So next step is to square roots, take a square root of 16, right? So you can check that this is also a field, which is 1 minus 1, 4 and minus 4. Okay, and you can also keep extending, right? So this guy is what is still 16, and this guy is 13, right? So you can take 1, 16, and then you take a square root of this is your original one, right? And then take the square root of these 2, you get 2 and minus 2, and then take the square root of minus 4. So minus 4 is what? Right, so minus 4, you can negative 4 is basically 13, right? Mod 7. So 64 mod 7. Okay, so you can take 8 and negative 8. Right, so now you have, now this is the Galois group. Okay, so Galois group, and then this is your field extension. Okay, so you start from Q, right? So this guy become the Q, right? So this guy, all the larger group become, this is the Galois group of this Q alpha with this. And then you take all the subfield extension, right? And this guy will produce something which in the middle, right? So you can find the first guy, which is A1. You add join this dimension 2, and you add join A1 and A2, add join become 2, and you add join the A1 and A2 and A3, which add join 2. Okay, so this is the construction. Okay, so basically you can go to Wikipedia and type the seven regular polygon, and you can find that cosine 2 pi divided by 7 actually can be written as the plus or minus times something and the square root of something, which is very complicated but still solved. So now you can see all these tricks should generalize for the for the different kind of number field, such that you can find something, take a square roots, and for that one you can also find square roots and keep going. So this is the general strategy that how to construct field extension. So this is why quick introduction for how to do this. Yeah, that's it. And yeah, see you guys next videos.